Okay, let's begin. All right, this is the PFC and Python course. Um, my name is Derek Blanksma. I'm a software engineer at ITASCA, and I've had experience developing and using PFC as well as Python. And today we're going to give a brief introduction on these two concepts. All right, so let's proceed. So I'll give a little bit more of a intro about myself. So yeah, like I said, I am a software engineer at ITASCA. I started as a consultant and did that for a number of years. I've used pretty much all our codes in consulting. I use Flag 3D, 3DEC, and PFC. I transitioned over to development about 4 years ago. Currently primarily developing in Flag 2D, but occasionally in PFC. I do a lot of technical support for codes as well, including PFC. So if you ever have a question, I'll probably be the one answering it. Okay, so that's an introduction about me. So let's talk a little bit about about PFC and Python, about what we're gonna talk about in the next 30 to 45 minutes. Okay, so this is kind of how it's going to go down. Like I said, this is not a very extensive long course. We're going to keep it short and sweet and just touch on the main concepts. So we're going to start with a little bit of what we need to know, a brief introduction about Python. Python is obviously a scripting language developed by hundreds, if not thousands, of developers. It's very extensive. It, I believe, is the most popular scripting language as of today. So we'll talk a little bit about the high-level stuff with Python. Then we'll move into documentation and support. Throughout a lot of this talk, I'll be referring back to our documentation that has all the information we might need to find different Python methods, or examples are very important. So I'm gonna show you how to navigate that documentation set. Then we're going to talk about Python versus Fish. Is one better than the other? We get this question a lot. There's not a lot to say here, but there are some important concepts. So we'll discuss that. And then we'll end with example applications. We'll go through kind of a line by line. I'll open up PFC. I'll type out the code. You can follow along. You can do the same thing I'm doing. And it's a kind of a way to see how we use Python in PFC. All the example applications are on are in the documentation on the website, and I'll give you links to all that. Okay, so let's begin. All right, so Python, like I said, is a programming language developed by hundreds and hundreds of people, companies, for a number of years. We decided years back that we wanted to embed the language into our codes. And this would give people a lot of flexibility with what they can do and open up the vast library of Python into our codes. Currently, Python is embedded inside PFC, Flag 3D, and 3DEC. And not listed here, Flag 2D as well, which is a new release coming out this month. Python is embedded in that code as well. I won't go into just reading off the words here because I basically summarized that. So we'll go right into Python programming and talking a little bit about the basics. So I'm going to pull up this link. We'll move this over here. Every link that I'm going to go to is primarily in our documentation, and I'll talk a little bit about documentation, navigating, seeing what's all there in there, finding what you need shortly. But for now, we're just going to talk about what is Python and what are some good resources to teach us more about Python. A good place to start will be here, Introduction to Python Programming. So what we give here is a very brief introduction. We talk about basic types. Let's see what's in here. Basic types, lists, tuples, and dictionaries. And I'm not going to go into every detail about these things. That's really not the point of this tutorial. But I just want to show that there are this information is on our documentation set, and it's very useful because it covers the basics. What else? There's types such as, yes, I said lists, tuples, and dictionaries. You can go through all that. There's defining functions. We do that a lot in any kind of coding. And then a little more higher level would be error handling in Python, and it gives a brief overview of object-oriented programming. Not necessarily something you need to know for using Python and PFC, but it's there if you need it. Okay. So that's a brief introduction to Python. Let's see what's next. All right, so another or questions we get a lot about Python, I've listed here for your reference. And again, this is on our website, on our documentation set. The three top ones that we get, starting in no particular order here, is Python faster? A lot of times when we're modeling, we want to use a tool that allows our models to run quickly, thus saving us time and money ultimately. It's no direct answer, yes or no. I wish it was, but it's really not. What we pretty well surmised using Python in the last 5 to 10 years is that an equivalent function written in Fish compared to that written in Python will be about 10% faster. And of course, that all depends on what your function does. If, for example, it just simply loops through all the balls in your model and returns the ball ID, for example, Python on average will be about 10% faster. Now, there are a lot of other ways to make those operations much quicker. And Python, for example, offers something called NumPy arrays. NumPy is a module developed in this package called SciPy, and it's basically an array manipulation module. There's a link I've provided here at the very bottom that gives a great example on how to use NumPy arrays. We're not going to go into it because it's very detailed. The main concept is that instead of the concept of looping through individual objects, you create large arrays of those objects and you operate on the array itself, thus operating on all objects in that array in one shot. It can make your code much quicker, but it is more of a high-level concept. And if you're interested in that, I highly suggest to check out this link. All right, so I've been talking a little bit about modules in Python. So modules are really the whole concept of Python. Modules are something that's created by the developer, you, and it is a package of functions and variables, and it does a specific thing. Now, the nice thing about Python is since it's such an open source code, a lot of people have made different modules and they share them with the entire world. Some really great, some not so much. In the context of numerical modeling or something like PFC, we've included ones that we find very useful. And these modules include NumPy, which I just talked about, SciPy, a collection of scientific libraries, and then you can see the list, there's a few more. PyPy is a finite volume module, which does finite element analysis on its own. These are the ones that are included. The next question obviously is, can I use my own extension modules or some random module I found on the internet? And the short answer is yes, but you want to proceed with caution. Since it is a Python module, it will run in Python and run it exactly how you expect. The problem is we don't have near the resources to test every module out there. So you have to be a little careful about what it's going to do in line with PFC. Okay, so the next point I want to talk about is Python versus Fish. And we get this a lot about why do we have both, and do I need to know both? And the short answer is one is not recommended over the other. Fish is still there and fully capable of doing many, many things related to PFC. And as a developer and a consultant, I still use Fish for numerous tasks. The drawback is that Fish does not have the extensive library that Python is. And that's simply because here at ITASCA, we are developing Fish and we just don't have the other resources that something like Python has. Now, that's not to say it can't be fast or that it can't be useful. Fish can be very fast, especially in the multi-threading environment. However, Python, as I said, is very extensive in what it can do and what people have created. And it does have these packages such as NumPy that you can implement to make your code run very quickly. So yeah, that's all I'm going to say about Python versus Fish when it comes to which one is better. There really is no one answer that one is better than the other. Your application might work just fine using Fish, and it might work just fine using Python. Okay, the next 2 points are important, and it has to do with how Python data is saved after you issue a model new command. So as you know now, when you issue a model new, it clears all the state information and you're just left with a clean model. There's no Fish variables. There is no data saved anywhere. Now, Python we made a bit different largely because we want to run parametric studies when we issue a model new, that not all the state information is erased every time. So to do that, you give the command Python reset state false. So this changes the behavior so that Python state is not cleared by the model new or model restore commands. This is, like I said, largely done for parametric studies when we're running multiple simulations and we're issuing multiple model new commands. We still want some of that information to be saved in the next state. Typically, when you're running a Python code, using the Python reset state to false is done. It's done a lot, and it's pretty common practice to use it when using Python. And we'll show, and I'll show in an example where we'll use that. All right, so like I said, all the information that we have about Python and PFC is in our documentation set. And our documentation set is online. And we're going to go to that right now, and I'm going to show you a little bit how to navigate this set. All right. So here it is. This is our online documentation. This is the same documentation set as you get with your software from the help menu. The benefit here is that this is online and anyone can access it. So when you first open up the documentation set, you'll see a whole list you'll see a tree on the left-hand side, and everything that has to do with Python will be underneath the scripting heading. So underneath the scripting, like I said, we have two options. We have Fish and we have Python. We are interested in Python. The Python scripting is relevant in 3DEC, FLAC 3D, and PFC. And then we also have something called the ITASCA Common API, which I'll talk about in a little bit. But for now, what we're interested in is Python and PFC. So underneath this heading, you'll find basically a nice introduction about using Python with PFC. That's a simple example that we're going to actually run through at the latter part of this presentation. And it shows just simple operations we use in Python with PFC. The next headings are more advanced. So this next one called array style programming with PFC and NumPy is the example I mentioned earlier about using NumPy. It's fairly sophisticated, but it's a great example showing how to use this concept of NumPy arrays to make your code run very quickly. The next example is a UCS test with imported geometry. And then the last two, I would say, are quite high level, where you use a third-party SciPy package to import into PFC and do some modeling with that. And then last one is actually a GUI programming concept where you actually change a little bit of the GUI using Python. And it's very interesting, but it is a little more complex. And then lastly is the API specific to PFC in Python, which I am going to talk about right now. Okay, so this API, it's a little confusing at first, but with this is all the function definitions and the method definitions that are available in Python for PFC. So the way you look at this is that Python for PFC has a bunch of classes for all objects that are relevant to Python, or excuse me, for PFC. For example, some objects in PFC that you've learned about are balls, walls, and contacts. So when we're working in Python, we may want to query that information. You're going to have balls, you're going to have contacts. So you might ask, how do I get, say, the force on a specific ball-to-ball contact? Well, that's pretty easy. You'll basically look at these classes that are exactly that, a ball-to-ball contact. You click on it, and in it, you're going to find a bunch of functions that deal with ball-to-ball contacts. Let's see, such as finding N1, N2, there it is, you can look for the force in the global coordinate system and that kind of thing. So whenever you're using Python, you will be coming to this PFC Python API and trying to find out what functions you want to use. Let's see, some of the other ones will be, they'll have every one of them here, and basically everything in fish, like finding ball contacts in fish, you will also find those equivalent functions in Python. Some modules are a little more in-depth, where you can get ball arrays and ball arrays. These arrays are very useful for when doing array style programming with NumPy. And you can look at that NumPy example to see more about that. Okay, so that's a little bit about the PFC Python API. Just know that the API is the documentation where you will find the names of functions, what they do, what they return, for every part of Python and PFC. Okay. All right, so that's all I want to say about the documentation at this time. I will be jumping back to it here and there during the presentation, since it has pretty much all the information that you'll ever need to learn PFC, Python and PFC. All right, now let's actually do a little bit of work here. We're gonna do a simple example application. And this example of application is the first example actually in the Python for PFC documentation. All right, so what we're going to do is actually we're going to run it ourselves in PFC. And since this is the great thing about this is a recording, you can pause and follow what I'm doing and go at your own pace, however you wish. So I'm going to go through this example and we're going to talk a little bit about the commands that I issue, what they do, and what they produce. Okay, so by now you've all seen the main UI. You know how to create a data file. You know how to create a plot. You know how to get information from different objects. So we're going to do the same thing. We are going to make a data file. So we'll go File, New, or you can do it right here too. We'll go New, Data File. Now, when I say data file, it's literally that. It's not specific to a .dat. It can be a .f3 DAT. But in our case, working with Python, well, our data file is going to be a Python script. So let's call this test.py. The .py is the Python extension. The code will recognize from the .py that you are creating a Python data file. All right. So now that we have this Python data file, know that everything in this data file is now relevant to Python scripting. It is no longer fish scripting. So we can't say something like ball create. This will give an error. Ball create is specific to PFC. It's a command in PFC. This is not a Python script. All right. So let's just continue with the example application. So this is going to be universal to all Python code that you write. What we need to first do is import the ITASCA module. And the ITASCA module is everything that I just showed you on the documentation set under that API. So the ITASCA module includes the FACT3D API, 3DEC API, and PFC API. So the way you import modules in Python is you say import ITASCA, the name of the module, as IT. The as IT is just an abbreviation, so the module ITASCA will now be abbreviated as IT. Okay. Now what we're going to do, excuse me, is we're going to issue a command in Python. Now there are commands, of course, that you've learned in PFC. Ball create, for example, was one of them. And the way you issue a command in Python is that we say IT, because that's our ITASCA submodule, .command. And then inside the parentheses, you can type any PFC command you want. You could say ball create. Excuse me. Whenever a command is issued inside the parentheses from the module, it has to be, or inside the brackets, it has to be inside parentheses. You could say ball create, and it will create a ball. However, what we're doing now is we are going to set the Python state to false. Remember, by doing this, this means that when I issue a model new, none of the information before model new will be lost. So I'm going to say Python dash reset dash state dash false. Okay. And I'll show an example of why we do that here shortly. Okay, so these two lines are very typical about how you will start every Python script for PFC. There's pretty much not an instance where you will not use these two lines. Okay, so let's start by making a model, and we're going to generate just some balls and assign them a density. All right, so how do we do that? Like I said, whenever we type commands in Python, it's always our module ITASCA, which we abbreviated as it.command. And then we type all our commands inside the brackets. Now I'm going to do something a little fancy. I'm going to use 3 parentheses down here, and then 3 over here at the on next line. This basically allows me to type out commands line by line instead of one long string of commands. So the way we start, we create a model. Now we're basically in just PFC land. The way we start the model is we issue model new. Model new will clear out any state information specific to PFC, not specific to Python. So let's model new. And that's the way we start when we create a model. We want to typically let PFC know that this is let large string is on. And then the next thing we do is make a domain. And by now, I hope you have seen how to make domains. So we'll say model domain extent. And I'm just reading right off of and I'm going to just copy from this online example the extents. Okay, so these are the extents. Very small, but that's okay. All right, so now let's create a contact model in the CMAT. So you've discussed what the CMAT is at this point, and so let's just do that. So we say contact CMAT. And we're going to say default. What type of model? It'll be simple linear model. And we'll give a couple of properties here. I'm going to copy them. A normal stiffness of 1:1 with a damping normal ratio of 0.2. Okay. So now we've assigned that default slot in the CMAT. So that's what contacts of any type will be given. They'll be given the model linear with those properties. All right, so now let's generate some balls. So the way to create an assembly of balls is either you distribute them or you generate them. So what we're going to do is just do the simple generate command. And what we're going to do is make a nice cubic hexagonal arrangement of balls. So they're stacked right on top of each other and right next to each other. And excuse me. The way you do this is using the keyword cubic for cubic packing. And then you define the boundaries of the box. And then here we gave a radius of 1.25, e to the -3. This should generate somewhere in the order of 8,000 spherical balls all stacked on top of each other. All right, so lastly, let's give these balls a simple attribute. And that was density of 2,600. Okay, so I'm going to save that. Yeah. And let's run this. So like with your any data file, you can hit the green execute arrow, and it will run. Oh, we have a Python error. Let's take a look. It's saying the bad conversion of parameter number 1, Python reset state false. Looks like I might have error in what I wrote. Let's just copy it here, throw it here. Let's try that. Okay, I must have had a error in my syntax. I fix that, and I have another syntactical error. And I see it right there. So this list of warnings you will get, and this is just telling you that on line 3, we did issue the Python reset state false command. That's fine. Let's not show that again. Close that, but Python did find another error, and it looks like I have a misspelling default. Okay. Now let's run that again. Excellent. And the console, no errors were reported. And it did make it to our model generation, and you can see 8,000 balls were generated. Okay. Before I proceed, I do want to show you one very important piece of information is that everything that was output after we issue our commands is shown in the console. This is also true for the Python console. Right next to console, you'll find the Python console. And it's basically telling me the same thing that was printed in the consoles that, okay, errors were detected, we fixed them, great. Now, if you want to Python query Python data, we'll need to do it in the Python console. So if we create a variable in Python and we want to check what that variable is, you can use the Python console to do that. And we'll show that in a minute. Okay, so we didn't have any errors after we fixed the ones I made. So let's take a look to see if indeed we did create a model. All right, I'm gonna split my user interface here, and I like to have my text on the left, and I'm gonna create a plot. We'll call it new. Go to new plot. Plot 1 is fine name. We'll make that. What we create, all we created so far were some balls. So I'm gonna go down to my plot item list. The down arrow gives the most common plot items for PFC, and balls number 1. And there you can see 8,000 spherical hexagonally arranged balls. Excuse me, cubically arranged balls. Okay, so now let's say we want to print out some information. Typically, when you were before learning about Python, you would go to your console and say you would print something in the console line here to find some information, say about a ball or a contact. You do the same thing, but this time you use the Python console. And now in the Python console, excuse me, we're going to use Python code to find information. So let's do this. I want to know the number of balls in my model. Obviously, we know it's 8,000. It says it right here, but let's find a function, a built-in function that will give us that information. So whenever you're looking for a function for that information, remember we go to our documentation set. So I'm going to pull it over here. And as I mentioned before, all the definitions of functions will be in the PFC Python API. What we're interested in is finding the number of balls. All these classes have to do with contacts and other types of information. What we're interested in is the ball submodule. So let's click on that. If you just click on the ball submodule, you see in this tree there's all sorts of other things you can click on. But for now, all we're interested in is functions and classes for working with ITASCA balls. So right here, the second one, itasca.ball.count, returns an integer, and it gets the number of balls. That's what we want. It's back over here. So in the console, I'm going to say IT. Now remember, in the documentation I just showed, it called the submodule ITASCA. We renamed it. We gave it an alias of just IT. So all you have to do is IT dot ball dot count. And let's take a look to see if there were any arguments. ITASCA.count, no arguments needed. Okay, type that out, hit enter. Okay, so Python has processed our function and it's returned the number 8,000. And indeed, that is the number of balls we have. Okay, so let's take this a little further. Let's find some information about a single ball. Maybe we want to find some information about the ball with ID, or with an ID. All objects have an ID, so all balls here have an ID. So we'll just go again. We'll look at the Python PFC API. So let's see. The way you retrieve a specific ball is using this particular function, ITASCA.ball.find. So what does it return? It returns a ball object. It will get the ball object with the given ID number. So let's try that. In the console, let's create a new variable. We're just going to call it ball will equal it.ball.find, requires an ID. Let's say ID 1. Enter. Now nothing was shown in the console. That's because we are just assigning the information from it.ball.find to the variable ball. Now, if you want to see what information ball holds, the way you do that in Python is with the print command, and it is simply print parentheses ball. And below, it's showing what information is returned. Ball is an ITASCA.ball object. It's given it's an address and memory, and it's ID 1. So that's the information that is returned from the it.ball.find function. Okay. So now that we've assigned this variable that information, we can actually take it a step further, and we can determine the radius of this particular ball. The way you do that, much like in fish, is you say ball.radius. So this will return the radius of the ball with ID 1, because remember here, we assigned ball to be the ball with ID 1. And there you can see that it has the radius that we specified here on line 12 in our Python script. Okay. All right, so let's keep going with this, and let's see what else we can do in Python. So now I'm just going to continue in my script, because all these variables and these functions that I wrote on the Python console could have been written in the test script here, and they would have done the exact same thing. I was just using the Python console to show you how you can basically use it. So let's continue with our script, and let's find the sum of all the radii in this model. It'd be a simple calculation, but for practical purposes, let's see how we would do this in Python. So let's start by creating a variable. Let's call it radius sum. And let's initialize it to 0. Now, let's create a for loop, a loop that will loop through each ball, and we will find its radius, and we'll increment the radius each time. The way you create loops, and there's very many ways to create loops in Python, but that's a very simple way, is the simple for loop. So we say for some object or some value, we'll call it B for ball, for some ball in a list. Well, now we need a list. We haven't created one, but the nice thing about Python is that they automatically create these lists of objects when we create them. So what we need is a list of balls. So let's take a look at the PFC Python API. What we need is a list of balls. So here on the left side of the tree, we're still looking at balls. We're not looking at contacts or anything like that. We're looking at balls. So if you scroll down, we see we have ball energy, we have ball find, which we used. We have ball in a box, finds objects in a box. And here we go, ITASCA.ball.list. So this returns a ball iterator object. It's basically a list of all the balls in the model. So let's write that in our for loop. So for each ball in ball, excuse me, let's bring it up here so I'll make sure I get it right. In it.ball.list, no arguments. And the syntax for the for loops in Python ends the first line with a colon. The next line must be spaced 4 times or tab spaced. And this is how Python recognizes the next line for any kind, for a function or for a for loop or anything like that. You remember in Fish, we use brackets to specify the beginning and ends of functions or the beginning and ends of loops. Actually, we use end loop for the end of a loop. Python uses everything based on the tab or the indentation. So we'll say for each ball B in it.ball.list, we will set the radius, radius sum to B, because remember B is now just a ball from the list, dot radius, which we looked at already. It takes no arguments. And since we're going to be incrementing, the shorthand for incrementing a variable is just the plus equal sign. Okay. So let's I'm going to save my script, my Python script. I'm going to run it. I just did that, and Python is saying no errors were produced. And you can even go to the console, no errors were produced. Okay, so let's check out this radius sum to see if indeed it did increment as we expect. One thing to note that when you're scripting in Fish or when you have your data file as a Fish data file, you will have all your global variables here. That's not the case for Python. But we can query it here in the console. So let's say to find information, to print information in Python, it's always print with the parentheses. All right, so print, let's call it, we know what the name is, variable radius sum. And there it is. The summation is approximately 10. Okay. So that brings us basically to the end of this part of the example application, where we created a model. We've done some very low-level querying of data and determining different information from the model. Okay. So let's continue on in the example, and we're gonna see what happens when we cycle. So to get out of the for loop, remember, if I was to write any code here, for example, we would still be in the for loop. To get out of it, we simply get out of the indent, and I'll go down here. So how do we cycle? This model will certainly cycle. We've assigned ball density. We've given a contact model. So let's do that. Remember, in Python, we start every command with it.command, parentheses, model, cycle 1. Okay. And the way to run one line at a time in a Python script is the same as in your data files for Fish. You simply select the line and click this button, execute the selected command. Now nothing really showed up on the Python console. However, it did show up on the console saying that this was the command issued, model cycle 1, and it gives information for the total number of cycles, the time step, and the running clock. Okay. So now what we're going to do is, let's see, we're going to find a ball at a particular point in space, and we're going to determine its position. So the way we can do that is the next line. We'll say B, we'll make a variable B, or let's just call it ball like we did before. We'll say ball will equal if we're finding a function, it's going to start with it dot ball dot near. And the near function is in the PFC Python API, and you can look it up. But I know that this is how we find a ball near a certain position. And it takes a vector, and it takes a three-dimensional vector with X, Y, Z components. So we just want to find a ball that's the closest to the origin. All right. And then we want to find out B dot position. Basically, what that is going to do is, ball dot position. All that's going to do is it's going to report what the position of the ball we found at nearest the location of 0, 0, 0. Let's execute those two lines. Okay. Oh, I did not print the position onto the console. So the way we do that is let's just go to the console and say, let's print ball dot position. And indeed, that's the ball that is closest to the origin. Okay. Now let's talk a little bit about contacts. So since we cycled once, the contact detection logic will be invoked, and all contacts will be given the contact model based on what we provided in the CMAT. So let's look at that over here. So let's hide the balls. Let's show the contacts. And then the ND, there are 12,000 contacts. They're all shown here. Okay. Say, for example, now that we want to find the number of contacts on a specific ball. And let's say it's the ball that we defined here at the location near the origin. So you could, one would think, is say we want ball dot contacts. And in fact, let's print that off. And we can write the print on the print command string to the script, and that's fine. So we want ball dot contacts. Remember, ball in this case is from the variable I just defined on line 22, ball contacts. So it's going to return the contacts on that specific ball. Okay, so I'm just going to execute that. Okay, what do we see here? And something did show up in the console because we said print, and it's actually right here. The previous line was from when I wrote the print to print the ball position. It looks like a lot of garbage, but what it's actually returning is the type, the address and memory, and the ID of all the contacts that are associated with ball. And it returns it as a list. So if we want to say, just find how all we're interested is just the number of contacts on that specific ball, what we can say is we can use the Python intrinsic function and this is a function that is built by Python, not by us, called length, L-E-N. Len basically finds the length of a list, like of a Python list object. So let's try that. So I'm just going to execute that line. And sure enough, in the console, it shows us that the number of contacts associated with ball is 6. And that makes sense because this is a cubic arrangement where one ball has 6 balls on surrounding it, and thus 6 contacts in a cubic arrangement. Okay. So let's go a step further. So like what we did with looping through balls, we can also loop through contacts. So let's do the same thing. Let's say use a simple loop. I'll say for. We'll give the name to the objects we're going to loop through, and I'm going to call it CLNT. We'll just call it contact for contact, and ball.contacts. Remember, we can do this because ball.contacts just returns a list, and what we're going to do is we're going to loop through the list. So we're going to loop through each one of those. Python syntax requires a colon at the end. Next line, tab. We're going to print some information. And the print function can take any type, strings, numbers, all sorts of different things. So we're going to say print contact with ID. Well, we're going to make it something called a placeholder. And the way you do a placeholder in Python is with the curly brackets. So we'll put a placeholder there, at, and a placeholder there. So we're going to print contact with ID at some position. So the way you do that is then we terminate the string. The print command allows this dot notation to add, we say format. And in the first placeholder, we're going to say the contact dot ID. Contact ID is a function from the Python PFC API. And in the second placeholder, this guy right here, we're going to say, what do we want? We want the position. So contact dot EOS is another function from Python PFC. And now let's terminate the last bracket. All right, so let's run those 2 lines, basically just the for loop. Execute that. Oh, and it looks like I do have an error. Looks like I'm missing yep, I am. I'm missing one more parenthesis. Let's add that. There we go. Now we have enough parentheses. Okay, let's execute that. And sure enough, here are the 6 listed contacts giving each ID and their position. Okay. Let's see, let's continue on. So the next part of the tutorial talks about a little bit more about querying data about the contacts. And I won't go into that because we pretty well have that under control or with balls, but you can go through the example and see for yourself. Let's do this. So now that we have some contacts, a common thing we want to know is about properties about contacts. So say, for example, we want to find the property of friction for a contact. The way you do that is you can say contact, let's see. Let's find a contact first. Let's say we're going to find a contact. We have a list of contacts were made in the for loop, but I'm just going to rewrite this variable to be, we'll say contact equals I think this is one ball.contact find, maybe with ID 1. Let's see what that does. It did not. Let's go back to our .contact.find. There we go. Let's execute that code. And it says function takes 2 arguments. Let's see, what argument did I miss? Let's go back to documentation. It says ID. Oh, here we go. Type, object type is the first argument, and then the ID is the second object argument. So get the context of the given type. Okay, the second argument is either an integer ID or a length. Okay, so we first need the type. So the type, capital maybe. There we go. Okay, so the type is actually it.ball.contact. Okay, so let's check that. Let's print contact. Indeed, there it is. ITASCA.ball.contact ID 1. Okay, let's continue on. Before, when I was using ball dash ball, when I had this value, this argument, this is type settings for fish actually, and not for Python. So the actual type is itasca.ball.contact. Okay, so let's go back to the tutorial. All right, so let's try find, let's print out the value of friction. So the contact dot to find a property, we use the property function, just prop, and we give as a string friction, shorthand for fric. So let's execute that. Oops, and I missed a parenthesis. Let's execute that. And the value returned is 0, which you'd expect because in our contact model or our CMAT, we did not assign any friction to the contacts. Say, for example, if we were to actually find a value that we have assigned, we can use Kn, for example, the stiffness. And what we get is 10, which we assigned. Okay. So that pretty much does it for for this example. I'm going to end it there because there's a lot more you can obviously do as far as finding information and querying different information in your model. I highly encourage you to look at the this example again. That is here in scripting underneath Python scripting, and then in PFC Python. You can go to the first subheading called using Python and PFC. And basically it goes through everything we talked about. There's a little more in-depth exercises here, specifically about using some fancy ways to manipulate lists in Python and that kind of thing, and then printing the information. I won't go into that in depth. It's just kind of a nice shorthand way of doing things with lists rather than looping through each individual object. It continues on to talk about the type system, which basically means what kind of types, which we had talked about, ball types or ball contact types, ball pebble contact types, and a plethora of other different types. And then it ends here with something called callback functions, and this might have been something that you ran into In Fish is that you can actually call functions while cycling. And this is useful because you can return data, or you can manipulate objects while cycling. One thing to know that doing such an operation can severely impact your runtime because you're stopping each cycle to run your function. And if that function, for example, loops through a million balls, it's going to take an extremely long time to run. So Python offers really quick ways to do callbacks. All right, so that pretty much ends the talk.